Hey everyone, and welcome. Today, we're going to break down one of the biggest, most fundamental ideas in all of calculus, the limit. Now, I know it can sound a little intimidating or abstract, but trust me, it's actually this really cool and powerful idea that's all about one thing, getting super close to something.
You know, the entire concept of a limit really just boils down to this one simple question. What does it actually mean to be approaching something? We're not talking about actually getting there, but about the process of getting infinitely, unbelievably close to a point. So let's dive in and see what that really looks like.
All right, so here's our game plan. First, we'll nail down what a limit actually is. Then we'll talk about why you have to look at it from two sides. After that, we'll check out what happens when limits just, well, don't exist. And finally, we'll get into some really powerful tools, the 7 indeterminate forms and some super helpful trig shortcuts. Okay, let's get right into it. A limit is all about describing what value a function is heading towards as its input gets closer and closer to some number. The key phrase there is closer and closer. Think about it like this. We don't actually care if the function ever reaches that exact point. We just care about the value it's homing in on. It's all about the journey, not the destination. Now, to really figure out where a function is going, you've got to be a bit of a detective. You can't just look from one direction. You have to investigate from both sides of the point you're interested in. It's kind of like approaching an intersection in your car, right? You never just look to the left, you have to check for traffic coming from the right, too. Same idea here. In math, we have a name for this, the left-hand and right-hand limits. The left-hand limit, which you can spot by that little minus sign, is what happens when we sneak up on our target value a using numbers that are just a tiny bit smaller. And the right-hand limit, with the plus sign, is when we come at it from the other side, using numbers that are just a little bit bigger. And this, right here, is the golden rule. Seriously, if you remember one thing today, make it this. For a limit to officially exist at a point, the value you're heading toward from the left has to be the exact same value you're heading toward from the right. Both paths have to lead to the exact same spot. If they don't, we've got a problem.
So you might be asking, what happens when those two paths don't meet up? Well, that's exactly when we say the limit does not exist. It's that simple. Let's look at a couple of classic examples where this happens.
First up, we've got the greatest integer function, which some people call the floor function. Basically, whatever number you put in, it rounds it down to the nearest integer. We're going to see what happens as our input x gets really close to 3. Okay, check this out. Let's use our two-sided approach. First, let's come from the right-hand limit. Imagine we're plugging in numbers like 3.1 or 3.01 or 3.0001. What does the function do? It rounds them all down to 3. Easy enough. But now let's sneak up from the left side with numbers like 2.9 or 2.99 or 2.999. The function takes all of those and rounds them down to 2. And there it is, a perfect example of our rule in action. The left-hand limit is 2. The right-hand limit is 3. Are they the same? Nope, not even close. So we can say with total confidence that the limit of this function as x approaches 3 simply does not exist.
All right, ready for another one? Let's look at the limit of the absolute value of x, divided by x as x gets closer and closer to 0. This one is a classic, and it's a little bit sneaky. Let's break it down again. Let's start with the right-hand limit. We're using tiny positive numbers. The absolute value of a positive number is just the number itself. So we basically have x divided by x, which is always 1. But what about the left-hand limit? Now we're using tiny negative numbers. The absolute value of a negative number makes it positive. So on top we have a positive value, but on the bottom we still have our original negative value. And a positive divided by a negative gives us -1. So what do we have? The right side is heading towards 1, but the left side is heading towards -1. Since -1 most definitely does not equal +1, the two paths don't meet up. And you know what that means? The overall limit at x equals 0 does not exist. Okay, so sometimes when you first try to solve a limit, you'll plug in the number and get a really weird answer, something like 0 divided by 0. Now these aren't your final answers. Think of them as signals, like a little red flag from the math world telling you, hey, you need to do more work here. Dig a little deeper.
And it turns out, in calculus, there are exactly 7 of these special cases. We call them indeterminate forms, because just by looking at them, you can't determine their actual value.
And here they are, the whole gang. You've got classics like 0 divided by 0 and infinity over infinity. They're called indeterminate because they represent a kind of mathematical tug of war. For example, in 0 over 0, the numerator is trying to pull the whole thing down to 0, but the denominator is trying to make it explode towards infinity.
So who wins? We don't know. When you see one of these, it means you have to use a different strategy to find out which force is stronger and what the true limit is.
Now, to help us win some of those tug-of-war battles, there are some famous, well-known limits that are just so useful to have in your back pocket. They pop up all the time, especially when you're dealing with anything involving trigonometry.
Here are 3 of the big ones. The limit of sine of x over x as x approaches 0 is 1. This one is huge. It's the foundation for so many other trig limits. Then you have the limit of tan of x over x, which is also 1. And another really handy one is the limit of 1 minus cosine of x all over x squared, which comes out to 1/2. Honestly, just memorizing these can feel like a superpower and save you a ton of time down the road.
So let's recap. We've got our golden rule. For a limit to exist, the left has to equal the right. We know the warning signs, those 7 indeterminate forms. But this all leads to one final, really important question. What do we do when we actually run into one of those 7 forms? What are the special techniques we need to use to solve them and find the real limit? Well, figuring that out is the very next step on your journey to mastering calculus.